Welcome back to The Explainer. I am so thrilled to have you here today. We're going to do something really fun. We are completely demystifying two of the most heavily tested, fundamentally crucial topics in chemistry, electrolysis and energetics. Look, if you've ever felt like chemistry is just this chaotic collection of random rules, believe me, you are not alone. But today, we're breaking these concepts down using crystal clear visual rules and some really simple dichotomies. We're going to turn all that abstract theory into a highly structured, logical system that you can actually visualize and remember. So let's jump right in.
Okay, so here's our agenda. Think of this as your ultimate visual cheat sheet. First, we'll hit the basics of electrolysis. Number 2, we're looking at cathodes, anodes, and gases. 3, we're diving into exothermic versus endothermic reactions. And finally, number 4, lowering the energy barrier. Let's kick things off with Section 1, the basics of electrolysis, decomposing compounds.
All right, so at its core, chemistry is so often about this central challenge, splitting incredibly stubborn compounds. Some atoms are locked together so tightly in these ionic bonds that they absolutely refuse to let go of one another under normal conditions. You know, they're chemically happy, they're stable, and they're completely uncooperative. So how do we force them apart? Well, we bring out the heavy artillery. And that brings us to our fundamental definition here. Electrolysis is the decomposition of an ionic compound using a direct current of electricity passed through a liquid electrolyte. Notice the phrasing there. We're taking a liquid electrolyte, which is really just our stubborn compound melted down or dissolved so its ions can physically move around, and we're forcing a chemical split by blasting a direct electrical current straight through it. We are literally using the brute force of electricity to tear these stable compounds apart.
Now, what's really interesting about this is the two arenas where this battle actually takes place, the cathode and the anode. To make sense of this, I want you to think of electrons as the absolute currency of chemistry. Over at the cathode, which is our negative electrode, we have reduction taking place. This is where positive cations arrive, and essentially, they get paid, right? They gain electrons. Now flip over to the anode, our positive electrode, and we have oxidation. Think of this as the tax collector. Negative anions arrive here and they are forced to lose their electrons. They give up their chemical currency. So gaining wealth is reduction, losing wealth is oxidation. It's this perfect, continuous transaction.
Moving right along to Section 2, cathodes, anodes, and gases. Visible reactions.
And this brilliantly illustrates what happens next. See, electrons are completely invisible. We can't literally watch this microscopic currency exchanging hands. But chemistry is a physical science, right? And when we run these reactions in aqueous solutions, meaning our compounds are dissolved in water, we get this incredibly tangible, sensory evidence. Water actually brings its own ions to the party, which creates competition. If your solution contains highly reactive metal ions, say sodium or potassium, they just hang out and stay in solution. Instead, hydrogen gas is preferentially discharged at the cathode. Now, how do we prove that's happening? You hold a lighted splint to the gas, and you'll hear this fantastic, sharp, distinct pop sound. It's iconic. On the flip side, if the solution is very dilute, or if it contains stubborn ions like sulfate or nitrate, oxygen gas is preferentially discharged over at the anode. To test for this, you take a wooden splint that is just barely glowing red, plunge it into the gas, and watch it miraculously burst back into a bright flame. It's super sensory, it's absolute, and it perfectly proves that the invisible electron exchange is actually happening right in front of us.
But, as anyone studying this stuff knows, you absolutely need a bulletproof mental rulebook. And that means we have to acknowledge the primary exception. If you've got highly concentrated halide ions, like a super dense chloride solution, well, the rules kind of bend. In this high concentration environment, those halides muscle their way right to the front of the line. So they're discharged as halogens at the anode rather than oxygen. It's a really crucial caveat to keep your understanding totally accurate.
Let's move along and see how this builds. We're transitioning here from the mechanisms of electrolysis, the electrical forcing of bonds, straight into our thermal rules. So we're shifting our focus from electrical energy to thermal energy. But the underlying theme, it remains exactly the same. The whole shebang is all about the movement and transformation of energy during a chemical reaction.
Which brings us to Section 3, exothermic versus endothermic reactions, the energetic tug of war.
So, if electrolysis was all about using electricity to force a reaction, thermal reactions are much more about the natural, energetic tug of war that happens when bonds are broken and formed. It is literally a battle of heat. The crucial point here is understanding the balance sheet of this tug of war. Let's look at the exothermic side first. These reactions release thermal energy into their surroundings. You can actually feel the test tube get hot in your hand. It's a very measurable temperature rise. Why does that happen? Because the energy released when new, stable bonds form is vastly greater than the energy it took to break the old ones. Bringing back our currency analogy for a second, the system is spending its excess wealth out into the environment. That's why it features a mathematically negative enthalpy change, or minus delta H. Now contrast that with endothermic reactions. These absorb thermal energy. The test tube actually gets cold. The system is incredibly greedy here. The energy required to break those initial bonds is overwhelmingly greater than what gets released later on. So it literally steals heat from the surroundings to make up the difference. It gains energy, resulting in a positive enthalpy change, or plus delta H.
All right, our final stop is section 4, lowering the energy barrier, manipulating reactions. So far, we've laid out the rigid rules of electrical and thermal energy. But here's the thing. Chemists are not passive observers. We don't just sit back and watch these reactions happen. We actively manipulate them, right? We want to rig the game in our favor. So I'll pose this question directly to you. How do we make these reactions happen easier? Think about it. If a reaction requires just a massive amount of energy to get started, if it's stubbornly sitting there doing absolutely nothing, what is the ultimate chemical solution to force its hand without just pumping it full of dangerous amounts of heat or electricity?
To answer that, we first have to introduce the villain of our story, activation energy. By definition, this is the minimum kinetic energy that colliding reactant particles absolutely must possess to successfully react. I want you to picture it as this massive, invisible mountain sitting right in the middle of your chemical pathway. Even if a reaction wants to happen, even if it'll eventually release a ton of energy, those particles first have to crash into each other with enough force to scale that massive peak. If they don't hit that minimum kinetic energy, they just bounce off each other harmlessly. The barrier stands firm.
But enter the hero of chemistry, the catalyst. I absolutely love this concept. I like to call it the catalyst cheat code because of how elegantly it solves the problem. A catalyst doesn't just magically give particles more energy to climb the mountain. Instead, it provides an entirely alternative reaction pathway. It effectively digs a tunnel right through the base of the mountain, creating a completely new route that features a significantly lower activation energy. So suddenly, particles that were just bouncing off each other have more than enough energy to slip right through this new, low-energy tunnel. And honestly, the best part? The catalyst is not chemically consumed in the process. It just sits there, keeping this tunnel open again and again and again, endlessly speeding up the reaction without ever being used up itself. It's a total game changer.
Which leaves us with a truly fascinating paradox to ponder. We've seen how electrons act as currency, right? We've seen how heat is exchanged in this grand tug-of-war and how a catalyst acts as an unbreakable cheat code. But think about this for a second. If a catalyst perpetually lowers the energy barrier, allowing reactions to flow rapidly, and it is entirely immune to being consumed, what physically limits its power in an infinite cycle of energy? Why doesn't it just accelerate reactions until the universe literally runs out of reactants? I want you to let that question simmer. Keep looking at the systems around you, keep questioning the rules, and I will catch you in the next explainer.